Here we want to find the equation of motion of a simple pendulum using Lagrange's formulation. I am Mr. Dinesh Bobde, working as assistant professor at NB Mehta Science College, Bordi district, Palghar. As we want to find equation of motion of a simple pendulum using Lagrange's formulation, to find out equation of motion, we should know the degrees of freedom, and to find the degrees of freedom we should know constant equations and number of particles or masses present in the system. So let us see the arrangement of the simple pendulum is shown here. A simple pendulum consisting of one mass is attached with a rigid support through an inaccessible string. This string having a constant length L is shown here. When we give oscillations to the pendulum or to the mass, it travels along this path is shown here. Now here number of masses for the system are 1 m. Constant equations are L equal to constant and theta equal to constant. During the motion L is constant and phi is constant. During motion only theta is changing. This theta is only changing. That is, there is no motion along phi is constant. Along this plane phi equal to constant and L equal to constant. There is no motion along L, therefore L is constant. Now we want to find degrees of freedom for this system. F is equal to 3n minus k is equal to 3 into 1, that is, what is 1? N. N is number of masses present in the system. It is 1, and k is degrees of k is number of constant equations. Here are 2. Therefore, degrees of freedom becomes 1. Degrees of freedom become 1. Now kinetic energy of mass m is T equal to 1 half m square equal to half m L square theta dot square. We can find easily the equation of motion of a simple pendulum by using spherical polar coordinates rather than Cartesian coordinates, because Cartesian coordinates x and y are linked to this length L. Both are changing, but L is constant during the motion. That is, x and y coordinates of the Cartesian coordinate system are related to L, and they gives one equation, L square equal to x square plus y square. And we know here is degree of freedom is only 1, but by using Cartesian coordinate system we get 2 equations, and therefore it is not convenient to use Cartesian coordinate system. Therefore you have to use spherical polar coordinate system here to explain or to obtain degrees of equation of motion of a simple pendulum. We know we can write T in spherical polar coordinate system. T is equal to 1 half m into bracket L dot square plus L square theta dot square plus L square sin square theta phi dot square. Here phi is constant, L is constant, therefore phi dot equal to 0, L dot equal to 0. Therefore in equation of T, first term and last third term become 0, and this only second term is appear here, is written over here, 1 half m L square theta dot square. The potential energy at point A is phi equal to mg into OB. See the potential energy at point A. At point A, vertically the mass has acquired this height OB. Therefore this is available length for a mass to move, and therefore you have to take this OB as a height. Therefore mg into OB is potential energy, and you can find out OB from this geometry. OC minus this CB here equal to mg. OC is total length of the string L, minus from the geometry we can find out BC. BC is L cos of theta here, and simplifying we get phi equal to mgl into 1 minus cos of theta. Then by knowing kinetic energy and potential energy, we can construct Lagrangian, that is L equal to T minus V, where T is 1/2 ml square theta dot square and V is mgl into 1 minus cos of theta, and here is minus, therefore minus mgl into 1 minus cos of theta. From this equation of L, we can find out derivative of Lagrangian with respect to theta and derivative of Lagrangian with respect to theta dot. Derivative of Lagrangian with respect to theta is minus mgl sine of theta. If you took this derivative of L with respect to theta, in first term there is no theta, therefore derivative of first term is 0. In second term here is 1, derivative of this 1 with respect to theta is 0, mgl is constant. Then third term mgl into cos of theta plus mgl into cos of theta, derivative of plus mgl into cos of theta with respect to theta is mgl sine of theta with minus sign, here is minus mgl sine theta. Then del by theta dot. If we took derivative of this L with respect to theta dot, we get 1/2 ml square, and derivative of theta dot is 2 theta dot, and therefore 2 get cancelled and we get ml square theta dot. This is del by theta dot. Then the Lagrange's equation of motion is, for theta coordinate, it is d by dt del by theta dot minus del by theta is equal to 0. The general form of Lagrange's equation of motion is d by dt del by qj dot minus del by qj equal to 0, where qj is generalized coordinate. Here is generalized coordinate is theta, that is degree of freedom is theta. By putting del by theta dot in the Lagrange's equation of here, we get d by dt ml square theta dot plus mgl sine of theta, that is del by theta is here, and in between there is minus sign, but minus mgl sine theta makes it positive, is equal to 0. Therefore ml square theta double dot, where by taking derivative of this with respect this term with respect to t, we get ml square theta double dot plus mgl sine theta equal to 0. By cancel out m on both sides, we get L square theta double dot plus GL sin theta equal to 0. Again by dividing L square on both sides, we will get theta double dot plus G by L sin square theta equal to 0. And if theta is very small, we can neglect sin theta, that is sin theta equal to theta, if theta is very small, and therefore theta double dot plus G by L theta equal to 0. This is the equation of motion for simple pendulum. If you see this equation of motion, see here the equation of motion, theta double dot plus G by L theta is equal to 0. In this equation there is only one coordinate present, which is theta, that is this is a degrees of freedom for the simple pendulum, or available coordinate for the motion is only theta, and this is quadratic equation. Okay, and it is second order differential equation, therefore we will get two solutions for this differential equation. The period of the oscillation of the mass is t equal to 2 pi upon under root L upon G, and the frequency of oscillation is nu equal to 1 over 2 pi square root G upon L. Okay, we stop here.